Okay, so the last one I wanted to show you here was this. And so this is stepping away from all these models all these approaches which essentially dig out hierarchical structures. Hierarchical structures are ubiquitous, fair enough, but not everything is hierarchical. And the approach here is to say, well, maybe we'll find all sorts of things. And so, for instance, here is a tree, a hierarchical thing, but it could be that and so this little example of species, I guess based on genetic similarity, I think in this case. But this is just a cartoon, right? It could be that they're in some circle structure. They could be actually isolated. And so there are these just different methods that bring them about. And so this paper, PNAS, it's now 10 years old, was trying to say, well, let's lift above hierarchies and just find whatever shape it is. And so they did some cool things. They have this little generative process of finding parts. So it is a top-down piece like the divisive methods that we saw with the betweenness approach. But you try these overall major patterns, and if they work, then you keep going. I don't think they allow for multi-level stuff. So if it starts off being a tree, they tend to think it's going to be a tree. Maybe I'm wrong there. You can see how it would generalize. All right. So they have this little piece. You have this little grammar of a graph, which is pretty cool, right? So parent node becomes two nodes, and then you try to find this deeper and deeper structure. So, just some examples. So you've got some underlying metric or some measure or distance between nodes, and it may be that you really have a network or you just have a difference between them, right? You just have, every pair has a distance between them. And so there's a facial structures, that turns out to be more on a grid, right? There's expression, so this is more on a grid. This for cities where you really just have a great circle distance or a very, very athletic, well-directed crow flies distance. And so that, once you do that, it lays it out on this mechanism or this algorithm will unpack a circular structure. These are shades of colors, the spectrum, right? So it's not going to break that down hierarchically. It's going to put it on literally a spectrum, which is what you want. These are based on people's measures of the left-rightness of Supreme Court justices, puts them on a 1D thing. And that's already imposed, right? They're already on a 1D spectrum, right? But you're feeding this thing in and it does that, it pops them out. It doesn't create a tree. Whereas this is, and I think this will be based on genetic information, it's going to create a tree structure. So this is a whole world of things you might need as well, right? If you feel like you really don't know what kind of structure there is, you want to allow for spectral things and all sorts of stuff, then this approach is sort of the start of that, I think. I just want to say something about this. The problem with this, of course, is that, as I said, it's the 1D structure is built in, right? And the left-right story for political space is a metaphor trap, right? So it was the French Parliament where eventually they started to call the ones over there the left and the ones over there the right, because it just made it easier to refer to these two groups that had separated. So it was a spatial metaphor trap, right? It was just sitting there, and 1D is easier than 2D. 2D, at least you have social and economic. You've probably seen some of those things, right? So, Hitler's here and Marx is here and so on. Gandhi's over here, and you do a little quiz and you accidentally give all your Facebook data up, but you also find out where you are in the political spectrum. And you could add a third one for foreign policy, all sorts of other things. But we're pretty comfortable with that. But then it becomes actually true, right? People do think there's just a 1D spectrum. And then you see people try to stick Rand Paul or someone in here somewhere, or they don't really know. They're going to stick them in because it's just true that it's a one-dimensional space, political space. And just to connect back to that historical thesaurus stuff, what we're trying to get to was metaphors, right? We're trying to just count metaphors in text. Can we do that? How many spatial metaphors are there? We have a ton of spatial metaphors, up, down, left, right? We impose that on things. Behind, you look forward and you're in time, and which is weird. And then there are sensory ones. This idea stinks. The thing is, metaphors are the scaffolding give us the scaffolding of knowledge. Anyway, this is a pretty interesting thing. Depending on how you approach it, you may end up with disconnected pieces, right, which may or may not feel right. So there's some tunability here. So that really goes from something different, right? There's actual partitions in this one to a tree. This is a slightly more complex tree, I suppose. So you got to be careful. This was a nice little test thing. So this is the true network, right? So they've made up these pretend networks. So these are isolated module structures. This is just everything is just on a little. It's just a straight right. So there's a ring here, and this is just a simple string of nodes. There's a tree structure here, and then what's much more of a spatial thing, a mesh. So this is if you this is what they did, right? So they said, make the algorithm believe it's a partition or a chain or a ring or a tree or a grid, and then run it on these real ones. And so the partition one finds that. This one, it's trying to get these extra little structures in here. The partition one does this weird thing for the ring, right? So it's it's just trying to find a partition. So it says, these are all little groups, but of course misses this very strong piece here. It does this to the tree, right? It's really this, but it's going to tell you that this is how it's shaped. And the mesh, it does this bananas thing here, right? So that goes on and on. There's some pretty, this is terrible, right? This is, the grid is trying to tell you, it's trying to get this back somehow, and it's just a complete failure. Some of these are quite amusing. So these ones are the ones that work, right? So this is grid trying to find a grid, tree trying to find a tree, ring trying to find a ring. So that diagonal, they're all right. And then, messes, and all the rest are messes. And then these are little fits. So, the tree actually does pretty well. The tree says the tree is the best one, but it's actually pretty happy with all of the others except for the partition version, what they call the partition. Grid finds a grid. See, it's not that much better. And this one, you can't really separate these. Okay, so I thought that was just an important thing to have been opened up, at least as a conceptually. I mean, it's PNAS, it got a good billing for it. That doesn't mean it's right. Back here? I think there's the number of features that they used from each. I think this is the genome, how much information. I think we could look it up, but I think that's the idea. And if they use more, then they get a more discerning kind of thing that comes out. This shouldn't be too much different. You see, of course, it's laid out differently, right? The birds are here, now they're over here, but they're all just in a little team. It's like birds, whoop, and then there's some subtlety. So these characters are separated off. Penguins over here, which is fair. Right, so it's just that there's more hierarchical structure, really. Yeah. Oh, penguins over here with a whale. Wow. So that didn't work out very well, did it? Where's the penguin up there? Yeah, well, I guess I'm sure this is genetic, but we'd have to look it up. But this is a strange team, really. We've got iguanas, penguins, and dolphins. Could be an excellent sitcom, but with some music at the start. What's that? What's that? You imagine the penguin in the confession video saying, I never really understood I was like a seal or whatever. Understanding their true selves. Whales and penguins, yes. All right, so I guess the summary there is that this is a huge and vast enterprise. There's a mind-boggling number of papers and then citations. It's just a huge thing. It's such an important thing to be able to do, and it could be that you have a network structure, so it's really, it's a network, right? The average degree is not that high. You have some network, and you want to use one of these methods to find the structure. Or it could be that you actually have measures of distance between every pair in your system, right? Which you would for this sort of thing. And so that's a different thing. You're still trying to find out if it's got a network structure, but there is a sense of a distance between all of them. Anyway, so those sort of two big categories, you want to feed them through some algorithm. And I don't know how much is loaded into something like Network X these days, but let us dangerously Network X, for example. It's usually, this is going to fail, I'm not going to be able to do it. Communities, it's often called communities, I guess. So here are some, right? Generators, yeah, I think that's probably what we just had. If there's a bipartite structure, you want to find that. Oh, wow. The validating partitions, right? Is this a good, what's the modularity measure of this thing? Lots of pieces. But that could be bigger. Clustering, that's not right. You'd think clustering was the right thing, but it's not. Yeah, okay. They could put more things in there. Yeah, it's certainly in the category of like comparing, now it's let's compare methods and mine is faster than yours sort of thing. That's how computer scientists like to play the game, right? All right. Okay, that's the finish of that. I'm going to just